Hey guys, so I want to make a clarification on some stuff with springs and then actually take a different approach to solving the spring problem we were taking a look at in class. Originally, I had a kind of idea of what I wanted to do with it, and then as going through in class, I kind of felt that it wasn't going as well as I thought it would in my head, and I think it's going to end up confusing a lot of more people than actually helping. So one of the things I did want to clear up is kind of the negative sign in the kx. That was a question brought up. So if you look up the spring equation, which is Hooke's law, you will often see it written like this. However, on the AP equation sheet, as pointed out, you see it written like this. So neither of these are right or wrong. They both do the same thing. So where the negative comes from, typically in the Hooke's law formula, is based off the direction in which the spring force acts. So for example, let's say we have a spring with no load on it. So this is here its equilibrium position. So the photo above it, A, shows an applied force. So I take it and I use a pulling force to the left and I stretch it some positional distance here, delta x. As a result, the spring force always acts in the direction opposite which the spring is displaced. So in order for this force to be negative, this negative sign here is added. Because delta x would be positive, this negative would get this force to come out with a negative value, indicating that it's going to the left. However, you don't need that negative sign. You can do it by the absolute values and then assign the negative after. So I could just say, well, the actual value of the force is k times delta x, that absolute value, and that gives me the absolute value of the force. And then at the end, I can say, well, since it's left, I'm going to make it negative. And you could do that in your sum of the forces, right? You could just have F minus Fs equals 0 if this thing is balanced, or in this case, they're calling that F applied. Now, oppositely, if I look at the one below here and instead I compress it this way, the spring force is going to act to the right. So here, because I have a negative compression, this X here would be negative, multiplied by that negative would give me a positive spring force or one that's acting to the right. But again, I could just do that, use only the absolute values and then assign the positive just by what direction it's going. So in this case, it would be Fs minus Fa equals 0. Since I've already accounted for the direction, I wouldn't need to worry about the negative and the kx. So either way is fine. So it's ultimately just personal preference. Now, one thing that was mentioned in the problem we looked at in class was this idea of the spring reaching equilibrium. And I realized I didn't define it as well as I would have liked to early on. So earlier on, I defined this position here as equilibrium, the point where the spring is not being stretched or compressed. And that is true, but equilibrium actually changes if you put something on the spring. And what I mean by that is, really what equilibrium is when the forces are balanced. So the net force acting on the system is 0. So illustrated here is actually two different equilibrium points. So here is the EQ, or the equilibrium point for just the spring. Point B, now we have taken a mass and we've hung it on the spring and it's come to equilibrium. This here is the equilibrium point for the mass spring system. Because once I put the mass on it and I've let it come to rest and hang, here, velocity is 0. So at that point, the forces have to be balanced, meaning the spring force up is balanced with the gravitational force down. It's in a state of balance, right? The net velocity is 0, the net force is 0, or the velocity is 0. So equilibrium changes depending on if there is a mass or something on the spring or not on the spring. Equilibrium is just where the forces are balanced. So here, the forces are balanced with nothing acting on it. And here, the forces are balanced for the mass spring system. So as soon as I introduce something else to the spring, it changes the system and therefore changes where its equilibrium is going to be. Now, and here's just another example. So, for example, here, this is its equilibrium for the spring mass system, where that they've called the upward force of the spring tension and the force of gravity down. So it's balanced, meaning that has no acceleration. Now at this point here, it's no longer at equilibrium. The tension force is not as great as the force of gravity downward. This thing has gone up and now it's starting to come back down. So it cannot be at equilibrium. And then once again here would be the equilibrium for just the spring system. Again, here's just another photo showing that same thing. Equilibrium for the spring, equilibrium for the spring mass system. Now, this also works with things that are not vertical springs. So, for example, this horizontal spring setup. Here is the equilibrium position for the spring mass system. So, if I displace it this way, it's no longer in equilibrium. If I apply a greater force, displacing it even more, it's no longer in equilibrium. Same thing, if it starts to be compressed, no longer in equilibrium, no longer in equilibrium. It's also showing how that force acts opposite of the direction which is compressed or stretched. So stretched to the right, force acts to the right, and we also see the proportionality as the greater that distance stretched, that more the force from F equals kx. So the force of the spring is proportional to the distance stretched or compressed. Now, another really important thing is actually taking a look at what is happening to the energy through all these points. So let's say we have this. So here we have A, B, C, D, and E. And these are the orders of the events happening. This point right here represents where the equilibrium position of the spring and mass would be together. So meaning that at that position, it's in a state of balance. The spring is not compressed, so there are no forces acting in the x direction, and the only forces in the y direction are Fn and Fg, which are balanced. What's going to happen is we're going to take that spring and we're going to stretch it this way. So now I have some positive horizontal displacement and a force acting this way. The spring is held at rest, so its velocity is 0. It's then let go. The spring force causes it to shoot towards the center, and now it has some velocity at the center point, and it keeps going until it is compressed as much as it can. The velocity is 0, and then it begins to head back to the right, once again passing through the equilibrium position and experiencing another max velocity until it returns to where it was stretched, velocity being 0. So an important thing for springs is that the maximum velocity occurs at the system's equilibrium position. So it will always have its max velocity if it's oscillating back and forth as it's passing through its equilibrium position. It has all this spring potential energy here, so then when it gets to the point of equilibrium position where there is no stretching occurring, then that means all that energy has to be kinetic energy. Its velocity is 0 at its turning points. So at this point here, it wants to turn around and head to the right. At this point here, it's going to want to turn around and head back to the left. And the other really important thing is that also at these turning points here, its elastic energy is at its maximum. And then same thing here, when velocity is maximum, that means its kinetic energy is at its max. And where velocity is 0, obviously its kinetic energy is at a minimum. Now, what would it look like if we actually graph this? So let's say we have points A, B, C, D, and E. So this axis here is going to represent energy in joules. Well, so as a spring oscillates back and forth, at point A, when it is stretched but not moving, it's going to have a maximum amount of spring potential energy. So let's say elastic is going to be blue and kinetic is going to be red. So I'm going to draw what both of these look like. So at point A, it's got maximum elastic energy and no kinetic energy. At point B, it's going to have maximum kinetic energy and it's going to have minimum potential or elastic potential energy because the spring will not be compressed. At point C, the spring is now compressed and it's come to a stop. So that means, again, I'm going to have 0 kinetic, maximum potential. At point D, I'm back to 0 elastic because it's no longer displaced from x equals 0, maximum kinetic, and then we're going to have, finally at point E, maximum elastic and minimum kinetic. Now, what do the lines look like here? Well, I know I have to get from A to B, but how is that going to look like? Is it going to look like just a straight line? Well, kinetic energy is a function of velocity squared. So that means it can't look like a linear line. It has to look like a squared function. So that means it's going to look like a parabola that looks like this. So my kinetic energy changes in this manner. And same thing for the elastic energy. Elastic energy is a function of that position squared. So likewise, it's going to have to start following a parabolic pattern. And I get this kind of nice oscillatory motion. And this also shows me my conservation of energy. So at the point where my elastic energy goes to a maximum, my kinetic energy has to drop off. Otherwise, this won't work. Now, what would the kinetic, or what would the total energy look like? So let's say I graph E total. Well, if I add the points, so I have max, min, at all these points, my total energy is just a flat line. And again, that's our conservation of energy. The amount of energy in the system is actually never changing. Where it's being stored is just different. So at point A, it's stored all in elastic and none in kinetic. Somewhere between A and B, like right around, I guess here, is the spring is compressed or stretched a little, and the block has some velocity. So it's being stored in a combination of both elastic and kinetic. So if I were to add those two storages together, I'd get this total point here. So we see that we have this kind of sine and cosine motion, and we'll actually describe that motion later in waves and sound when we actually deal with simple harmonic motion, not just in terms of energy. Now, this graph can actually get very complicated for something like a hanging spring. So let's say that I have a spring system here. So right at this point, this is the equilibrium system, equilibrium point for the mass spring system, meaning not just equilibrium for the spring, but the equilibrium after I've attached the mass to it. So let's say I'm going to then take it and I'm going to stretch it some distance here, x. And I'm holding it here, so it has 0 velocity. Let's call this here position A. I'm then going to let go of that spring. and it's going to start moving upward. It's going to return back to its equilibrium position here. Still going up. It's going to reach its point of maximum compression, and that's going to be now at a displacement of x again. And then it's going to repeat the cycle, right? So then I'm going to go back to here, back to its equilibrium position. Back a little below it. And let's see. And back to its point of kind of being maximally stretched. Again, at some distance, x. And so what we do know is at turning points, the velocity is 0. So that means its velocity is going to be 0 here, and its velocity is going to be 0 here. So I know that at this point, it has a max kinetic energy, or sorry, a minimum. And its elastic energy is a max, and that'd be the same here. EK is minimum. Its elastic energy is maximum. And then at this point up here, same thing. EK is min, elastic is max. And I know as it passes through its equilibrium position, so that would be here, I know the elastic is going to be a minimum, 0, and the kinetic energy is going to be at a maximum. Same thing here, it's passing back through its equilibrium position, so elastic energy is at a minimum, or 0, and its kinetic energy is at a maximum. So what if we graph these points? So let's say this is point A. Let's say this is point B. This one is C, D, and E. So same thing, I'm going to create a energy graph. So here is energy in joules. So we have A, B, C, D, and E. Well, the tough part here is now I also have gravitational potential energy. So I'm going to say, well, let's let this blue line here be where EG equals 0. Or Y equals 0. Let's go ahead and try to figure some of these things out. Well, let's start with kinetic energy. So we'll use kinetic energy in red again. So I know kinetic energy is going to be 0 at point A. I know it's going to be 0 at point E. And I know it's going to be 0 at point C here. All right, let's see. I know the elastic energy has to be a maximum at point A and at point E. But now how does that have to look? Well, I know that no matter what, my total energy in the system is going to be the same, right? The total energy never changes. Well, at point A here, its potential energy, gravitational potential energy is also 0. So that means all the energy has to actually be elastic. So if I'm drawing my elastic energy, I know that here is going to be the case, and then here that's going to be the case. And I know elastic energy is a minimum at point C, so it's actually 0 there as well. All right. So that tells me that my elastic energy is at least going to look like this. And again, I have that kind of parabolic motion or parabolic looking graph because this is an x squared function. It can't be linear. And now what about my gravitational energy? So I'm going to use yellow for that. Well, I know at A it's 0. I know at E it's 0. And I know at C it's a maximum, because C is when it has its greatest height above our equilibrium. And I can also see at point C that its kinetic and elastic energy is 0. So in order for the total energy to be the same, it's got to look like this. I know EG is mgh, so it's a linear function of h, meaning that from here to here, it's got to be linear. Now, my kinetic energy then, I know is going to be a maximum at B and a maximum at C. And in combination with these two things, it's got to add up to the total, so it can't be that big. So if it goes up here, then those things wouldn't add up. So it's going to have to be kind of somewhere below these points. So my kinetic energy actually has to look like this. And so you can kind of reason through what the energy graph should look like. Now, this one here is an example of a much harder one. Typically, though, you should be able to draw some things like this on the AP exam, where usually you only have to deal with drawing maybe one potential, the kinetic, and then the total energy. If you have to draw two potentials, it gets quite a bit harder. Now, kind of the practical behind all this. Well, it actually can make this problem a lot easier that we started in class. And so in class, we have this thing, it's being dropped, and the first part was determine the speed of the block the instant it hits the spring. So this part wasn't so bad, right? We said, hey, we're gonna set our y equals 0 point here, so EG equals 0. So then kind of the final position we're looking at is right when the block hits the spring. So if I'm creating a bar chart, we said, well, we have EK, EG, E elastic, EK, EG, E elastic. Our system here is the block can store energy, the spring can store energy, and the earth can store energy in terms of its gravitational field. Well, I know here if this is my initial state and this is my final state for the block. Originally, since it is dropped, it tells me that my initial velocity is 0. So here, 0 meters per second, meaning I have no kinetic energy. Now, it is a height above where I set the 0 potential, so it is going to have some gravitational energy. And then it's not going to have any elastic energy at its initial point because it's not compressing the spring. In its final state, it no longer has gravitational potential energy. And that's saying no compression occurs at this instance. Now, that means that there is no elastic energy. So all the energy has been transferred into kinetic. So that tells me that my energy initial must equal my energy final by the conservation of energy. And my initial gravitational energy must be equal to the final elastic energy stored in the system, or that mg delta y initial has to equal 1/2 kx squared. And we're asked to, not kx squared, 1/2 mv squared for kinetic energy. I don't know why I wrote elastic there. And solving for this, I see that the masses cancel. So let's see, this gives me that v squared equals 2g delta y initial. Get rid of that, or that v is going to be 2, 9.81, and then delta y 0.45. And this gives me, for at least part A, a velocity of 3 meters per second. So now part B, determine the force in the spring when the block reaches its equilibrium position. So now, what this is talking about is the spring block system reaches its equilibrium position. Now, if I kind of go back, the important thing here is that for the equilibrium position, that's when the forces are balanced. So it's saying it hits, makes contact, and the system of the spring block move, and now they're at a point where this statement must be true. The only forces acting on it are spring and gravitational. So I can make this statement here. So I'm gonna go over to this part, so B. EQ tells us F net is 0. So drawing a quick free body diagram, we've now gotten to the point where it's compressed downward, where FG and FS are equal, or that Fs minus Fg must be 0. So Fs and Fg are equal in value, or Fs equals mg, which is, see, the mass of the spring, or the mass of the block is 2 times 9.81, or Fs is 19.6 Newton. So that's an easy way you can do part B. Now, in terms of part C, determine the distance that the spring is compressed at its equilibrium position. Okay, so in class, I was going to show you how to do it with using, with setting the gravitational, or keeping the gravitational line of zero potential here, and show you how to do it with a kind of negative potential involved. Kind of thinking back on it, there are other better problems where I can show that they're a little easier to deal with. So instead, actually what you can do is just move where you want to call your line of zero potential and kind of treat part C as a new problem. So if we have the block here, its initial position, right? It's some height above this spring system. And then, so let's see, we had, and then it hits it, it's going to come to some unknown equilibrium position. And so now this here is its equilibrium position, and we have some unknown delta x. And we know we have this height here, 0.45 meters. Well, to make this easy, instead of setting my line of zero potential here and then dealing with this as being a negative height, I'm just also going to go ahead and set the line of zero potential here. So I'm going to say, well, let's just say here potential is 0, and so that position is where y equals 0. So creating a bar chart for this situation, where we have its kind of initial state and its final state. The system is still the same, so we have the block, spring, and earth. Now recall that when a spring system is kind of going through its equilibrium position, like it is here in motion, so we have the block that starts falling, it hits the spring, and this thing is moving downward, that at its position here, it's going to have some velocity. Now, because, let's see, what is, determine the distance the spring is compressed at its equilibrium position. Well, actually, I'm doing part D with this. So let me actually take a step back. I misread. So here we want to determine the distance that the spring is compressed at its equilibrium position. Well, the nice thing about its equilibrium position is we found that above, right? And we also know that Fs equals K delta X if you want to use the absolute value like on the AP exam. So we have 19.6 equals K delta X, or that delta X is 19.6 over K, which is 19.6 over 50. So delta X here is going to be 0.098 meters. All right, so then now for D, which I was doing ahead, sorry about that, is they want to know what is the velocity at this equilibrium position. Well, the speed of that block. So I know it's going to have some kinetic energy because they're asking me to find a velocity, possibly. So let's see. I know in my initial state. Let me go ahead. In the initial state, there is no kinetic energy, and there is no elastic energy. It's all gravitational energy. Now, when it hits the equilibrium position, the spring has been compressed a little, some distance delta X, so I know there is some sort of elastic energy, and there is some sort of kinetic energy because it's moving as it's compressed it. And there is no gravitational energy because I have decided that that new position is going to be 0. So from this, I would get my initial gravitational energy has to equal my final kinetic energy plus this final elastic energy. Let's see, I'm going to go on to one more page here. In other words, EG initial equals EK final plus E elastic final. Plugging in kind of our equations, we have mg delta y initial equals 1/2 mv final squared plus 1/2 k delta x squared. So here, I'm going to multiply both sides by 2, so I get 2 mg delta y initial mv final squared equals, or plus k delta x squared. So I want to find v final, so I'm going to subtract this kx to mg delta y initial minus k delta x squared equals mv final squared, or B final squared is 2mg delta y initial minus k delta x squared over m, and take that square root. Now here, I've got to plug everything in. So 2, let's see, mass is 2 kilos, G 9.81. Now delta y, this one is, I have to be careful with. Delta y is not just 0.45 anymore. It's the distance from here to here. So delta y is actually equal to h plus delta x, which is h 0.45 plus delta x, which we found over here, 0.098. So 0.45 plus 0.098. I'm gonna run out of room here, so I'm gonna move this over just a little, minus k, which is, it was 200 Newton meters. Also, I realize I have no idea why I wrote 50 there. But that answer, 0.098, is correct. So that's 200, 0.098, all over the mass again, which is 2, and we get a final velocity of 3.13 meters per second. So that part is definitely hard, even if you're not trying to do it without some potential energy, or some negative potential energy. Now, the final problem, is the speed of the block a maximum at the equilibrium position? Well, we know that it has to be a maximum because in general, when something is passing through, when a spring system that like this is passing through its equilibrium position, its velocity is at its maximum. Now, another way we can tell is, what if we were to draw a kind of force diagram? So we have this, right? And we said maybe here's its equilibrium position. So the question is then, is if it goes even further past its equilibrium position, will it be speeding up? And we know the answer is no, because it'll be at a maximum at its equilibrium, but here's the reason why. At its equilibrium, by definition, the force of the spring and the force of gravity must be equal. And at any point, and it's going to be moving with some velocity vector downward. Oh, I forgot we don't need to draw the velocity hats here, or the vector hats here, right? Because it's going to move downward. Once it's dropped, it moves downward. Now, if it keeps moving downward, the more that's compressed, the more the spring force is going to push back up. So that means if it keeps going down, we'll get into this situation where Fs is greater than Fg, which means we'll have a upward net force, and that means an acceleration this way. But it's still moving downward. So if the velocity and acceleration vectors don't match, it is now slowing down. So its equilibrium point will be where its maximum velocity is, because if it keeps going any further, the spring force upward is going to become greater than the gravitational force downward, and that's going to create an upward net force, resulting in acceleration in that same direction, opposite of the velocity vector, meaning that it is going to start decelerating. So yes. Occurs at that equilibrium position.